Hey everyone, welcome back to another episode of RoboPapers. Here we have this week we have Florent. He's going to tell us about video generative models. So would you like to take it away? Tell us a bit about yourself.
Yes, so I work at Valeo AI. Valeo AI is a small research lab within Valeo. Valeo is a big company that produces parts, automotive parts for OEMs and with international owned companies. But Valeo AI is specifically a small team within this big company that is dedicated to research and really open research. So we are really about publishing all of our work into conference like CoRL, CVPR, NeurIPS, etc. And for myself, I'm specifically focused for the last year on the world model project, which is all about having end-to-end driving model that have been trained at large scale, mostly on unannotated data. We don't like annotation, human annotation at all, so we try to move it.
So one of the advantages here is that it can all be kind of self-supervised based on just like training this predictive model. It's really exciting. I think that a lot of people have been kind of trying to make these world generative models work for policy training. So I'm excited to hear more about details. Would you like to, I guess, share your screen and introduce us to the work you're talking about?
I think I will start by providing some context, at least that will motivate the work, the main work that I will present after, that is VaViM and VaVAM. So first, well, to drive is a core need. It's to be able to represent your environment. That includes, well, first it's geometry, the road boundaries, and it also includes well, to be able to represent and detect the different agents in the scene, the vehicles, the pedestrians, vulnerable users, as well as the road directives, like traffic lights, lane markings, this kind of stuff that can have an impact on the behavior of the different agents in the scene. So classically, this has been done by explicitly representing everything in the scene, either by 2D or 3D detection or by semantic segmentation. So on the left, that we are seeing an early version of what was embedded in Teslas. So this was mostly powered by human annotation. And the issue with this kind of approach is that what is not defined does not exist. You really have an expert that define an ontology. And well, if it's not within this ontology, you can never detect it. The issue is
Can you
yes.
What's an example of something? I guess maybe you're about to get to this, but what's an example of something that doesn't exist that should?
Here, for example, you have plenty of examples. Like you have a box that just for a truck. So typically, when you try to detect things, you have priors on them, like a box, a fixed box that is aligned with the horizontal plane of the world. So this kind of stuff would be very difficult to detect. The lane, road, or markings on the road, well, can be not well as intended at how the law would intend it to be. A thread structure is not always well made. This kind of swerving trailer here, it's really difficult well to modelize with classic approaches. And then of course we have other elements like sometimes you may have a policeman, for example, handling the traffic instead of the traffic light, for example. And so you have many edge cases, and the world itself is ever changing. And so here it really shows the limit of, let's say, expert defined systems. And so that's why we would like to go toward more data-based really approaches that remove as much as possible any kind of expert biases.
So are you still trying to tackle the kind of object understanding problem? Purely so you started out talking about like 2D object detection. So we're talking about so is the problem still framed in your mind or best framed as like detecting important objects in 2D, or are you thinking more like pixels to actions?
Yes, really pixels to action, and well, you always have a representation in the middle. It's just that we are trying to have a representation that is more implicit rather than explicit.
Yeah.
Because with current approaches, usually you try to have representation that is interpretable by humans, which may have a lot of caveats. Well, usually it's not complete, which makes the system rigid and not able to adapt with how the world, the environment and the world changes. So indeed, with more implicit approach, we can move on to VaViM and VaVAM. It will be directly the method. So at the core, indeed, we want to pre-train. So that's only one way to do it. There are many ways to do it. So if you look at what has been done in the reinforcement learning literature with the world model-based approaches, and more specifically with the Dreamer theory, for example, you really try to learn a world model that will then allow you to plan and act. So this is our first step to go toward this kind of system. So far, in the literature, at least for autonomous driving, what is called world models are actually video generative models, sometimes conditioned on the actions, but they have never been used for action. So far, they have only been evaluated for the quality of the video they generate. We don't know anything about first, most of these models are closed source, so it's difficult for the community to study them. And then we don't know what are the learned representation. Are they good for driving? Can we use them? And so that's what we try to transfer here.
Right. So we've seen some things like publicized by companies like Wave do with their Gaia world model, and with 1X Technologies, the humanoid robotics company, doing world models. So like, but I guess so you're saying, so a lot of those are all obviously closed source, like you're saying. So I guess is that kind of the point, or how would you do you think that what you're doing here is probably similar to what those models are doing, or do you think it's more that like this is evident, this is how they aren't quite doing actionable policies with those, I guess? What is the
So if they are doing it, still not clear how. I guess they are, but they did not disclose at all how they are doing it. It's not clear if they are directly using this model like at inference time to take decision, or if they are only used at train time to supervise a smaller network, for a policy network that will then be embedded in a car. For example, indeed, the VaViM and VaVAM are inspired by two work. The first one, well, you cited one of them, is Gaia 1 from Wave, and the other one is P0 from Physical Intelligence for the action part.
Yeah.
So the VaViM here is really an autoregressive network. That's one way to train at large scale on video. The nice thing is that it mostly builds upon all of the advancements that we had in the last couple of years from LLM sites, because at its core, it's really just a GPT. You have here a specific kind of tokenizer that we use for image. It's typically a VQ VAE. For instance, we use a Lamagen, which is an improvement over VQ VAE. And we use the pre-trained Lamagen. Really, it's off the shelf, and we tokenize each frame independently. So it basically attributes to each patch of the image a unique integer, which corresponds to a learnable vector in the codebook, so which encodes what is in its patch. In this, usually also encodes some of its surrounding context. But this is mostly about visual compression. The point is to get a much more compact signal than the raw pixels from the video. So what you get is this sequence of now visual tokens, which is spatiotemporal. Like it's both here it's colored by its position in this spatiotemporal sequence, so it's across frames. And the GPT is pre-trained to predict the next token is a sequence. So it's really like LLMs. You have a causal mask, and you are learning by teacher forcing when you are trying to predict the next token in the sequence from all the past tokens.
Sorry, quick question. So your image tokenization scheme comes from, I didn't quite catch, but an off-the-shelf model, similar to an extension of VQVAE. How are you doing the temporal encoding? Because like you have lots of different frames that are all presumably highly correlated. A lot of the times, yeah. How are you handling that?
So for this, it was really simple. We use two kind of embedding. One that is spatial. So those are two different kind of learnable embedding. We disentangle the spatial and the temporal one.
So it's a learnable position encoding, essentially.
Yes.
Okay,
Yes.
gotcha. That both includes like X, Y, and T, essentially. Is that the
Yeah,
idea?
exactly.
Okay, awesome.
Okay. Well, for instance, I think it's for the spatial one. It's a one. Well, it doesn't make a difference, but we just do not disentangle the X and Y. Like we have one embedding per position per index. So we have the image to display is seen as a 1D sequence. That's
Makes
it.
sense.
But indeed, we have another one for the temporal one. So all of the spatial embedding are the same across frame. Well, between two frames, sorry. And the temporal one is the same across each patches of one frame, but different for each frame. And that's how then the networks manage to then extract spatial temporal patterns and try to learn how the dynamic of a driving scene typically evolves. And the hypothesis is that if the network manages to train for this task, then it means that it has learned a lot, or at least something about the geometry, the dynamic, and some of the semantics of the world, because it means that it predicted that cars on average will move this specific way, that pedestrians will move another way, and typically will be on crosswalks on the sides of the road. So it means that it already has learned something about how driving scenes behave. And this can then be used for the action expert. So we are still only at the beginning of really studying this kind of model. This project has already been a lot of engineering work on our side because we never scaled this kind of architecture. So we limited the study mostly because of time and resources to a qualitative one. So what you see here is an analysis of the representation of what this video model has learned. So we take arbitrarily here the 22 layer of the GPT, which produces a feature map, and then we project this feature map with a PCA into three components, and we map this component to RGB channel. And then this is overlaid over the image. And you can see that we can already observe some grouping. Like here, pedestrians are nicely clustered. Lane markings, road markings, are also nicely clustered. Even for building or trees, we have different we are grouped differently. So, which is really quite nice. We are really quite surprised by this and nicely pleased because we did not use any explicit supervision for this kind of behavior. This is only learned by really predicting the next frame, the next token in the sequence.
Yeah, Florent, maybe you can talk us through a little bit about the data that you used to go into training, the model. I understand one of them is actually significantly larger than the other, I think two, but the other two have more metadata around it. So maybe you can talk us through some of the findings and what kind of data you used.
So the biggest I think before the dataset that we use is called OpenDV, at least for the pre-training. And to give you some sense, I will detail it after, but to give you some sense of scale, this data set is about almost 2,000 hours of driving data. Whereas if we compiled all of the other publicly accessible data sets that are used by academia, the new plan, or data set, it amounts to about a few hundreds of hours. So to give you more details, this was it was from Open Drive Lab, University of Hong Kong, and Tübingen, and basically they scraped YouTube data, and you have entire channels that are really dedicated to driving, and the data is really clean. Like you have it's 4K videos, really stable, and just driving across different cities of the world. So this is what they state is a geographic distribution of their data, which is really new, at least in the academia world, where typically new scene and new plan are only in two. So this was an opportunity for us to really start to go large scale and see how large scale pre-training could help us learn good features for driving. Issue with this data is the main limitation, let's say, is it's only frontal camera. It is only one camera, and it's uncalibrated. We don't know how the camera is positioned on the vehicle. We do not have the ego motion of the vehicle because it's really just the video feed. Whereas in comparison for new scene and new plan, which is the second set of data that we use in our work, we have multiple camera, 6 and 8 respectively for new scene and new plan, fully calibrated and with the ego motion.
So how do you combine those like basically effectively two very different types of data set? You mentioned in your paper something about open loop and then closed loop. I think it ties into the various data set, right?
So this will be for after open loop and closed loop will be more about the evaluation. But how do we use these two data? First we use OpenDV, which is the largest one. Okay, uncalibrated, broad geographic distribution. That is I think we. But that will be the bulk of our pre-training. So first we train with entirely on OpenDV as a pre-training phase, so for VaViM, and then for a fine-tuning phase. So because we use learning rate scheduling, that's called warm-up stable decay. So it's really warm up, then you have a constant learning rate, and then for the last phase, you decay the learning rate. And so when we are in the stable phase, we use only OpenDV. That is the more general data. And then for the let's say 90% of the data is done within this regime. And then for the 10% remaining, where the learning rate is decay, it's also where we introduce the data set for the target distribution, because our evaluation framework, which we will talk about after, is a NeuroNCAP, and it's basically a nerve simulator which use scenes from new scenes. So we want our network to have good representation for this particular distribution, and so that's why we fine-tune for the less than 10% of the training on a mix of OpenDV, new plan, and new scene. We introduce a new plan because this will be also used, because new scene is too small. And so we combine it with new plan because, they have similar distribution in terms of geography. And we use them both for the imitation learning phase, which comes after the training of the video model. If you want, I can talk about this phase. It is how to, if that's fine, if you don't have any question on this, I can continue on the how do we translate it into actually a driving model.
Yeah, that sounds good.
Yeah, I think, yep.
So now at this point, we have a pre-trained VaViM. And so how do we use it? Well, to actually drive. Initially, we tried to continue with this approach of a fully tokenized GPT-based approach. And we basically took actions. Well, we have for the new plan and new scene dataset, we have the ego motion, which can be then translated into expert demonstration, like the action. And we tried initially to tokenize it. So you take the trajectory of the ego car and you learn a tokenizer on it. Again, with a VQ VAE or more recent approach like a FSQ or whatever, like quantization approach on it, to have tokens of trajectory, which will then be concatenated in this sequence before or after each frame. And that will allow both the network to predict the action and maybe condition the next frame. This did not work well for us. Certainly, we did not spend enough time at the time. But given the schedule of the project, we moved on. Well, P0 just was released, and it was really a good, seems to us as a good fit to our problem. Really, you will see in terms of image, it's really it's somewhat the same. Where P0 in their case used the pre-trained VLM, the pre-trained VIT that feeds features into Gemma backbone, and you have this action expert that I will detail just after, that takes features from this big vision language backbone to then condition on its action prediction. And that's really what the architecture is the same. Even this joint attention here is from P0. So this joint attention is just a mask that allows actions token to take information from the visual tokens, but not the other way around. Because here the representation is masked, and it also allows us to really do a KV caching. Because here, well, it's a flow matching network, so you need to do several forward paths here to start from a noised representation to the actual, to noise action to actual action to the prediction. So this is just a way, this denoising approach, just a way to handle the multimodality. Because let's say I have an obstacle that comes right at me, I can either avoid it from the left or from the right. If my goal, let's say, is behind this obstacle, and I do a simple regression, that I have a simple deterministic network, and my loss is a simple MSE, I will learn the average of my from the expert demonstration, and I will go right through right in the middle through the obstacle.
Yeah,
So
the average is the worst of.
yes. And so here the diffusion is just a way to learn the distribution and to sample from it. So to actually make a choice. We could, again, the discrete approach with a quantized-based trajectory, and which will then be a categorical distribution and sampling, is another way. It's just that for us, really the flow matching approach was really easy to, and it was really a one-shot approach. In the sense, sorry, that we only had to test it one time and it worked. So it really simplified the pipeline. The default, let's say, the limitation with this approach is that we do not use the predictive capabilities of VaViM. VaViM here is really used as a pre-trained backbone. So it is trained with this by forecasting the future, okay? But we do not use this at inference time. We really only use the features produced by this backbone. So as a feature, yes, sorry.
So the world model thing is just pre-training. So you're not really using it to actually like interactively generate training data or anything. It's mostly just this is a way of getting a really valuable set of features.
Indeed.
Yeah.
Indeed. I
Gotcha.
think we do not even talk about a world model. Like, I mean, that's what we tend towards, but in this paper, I don't think we even talk about a world model. But that's the spirit, at least at training time. And then for our future work, indeed, we want to integrate this. The current issue is that we have this model that is able to generate the future state of the world. Let's say we can condition it on the action so that we are able to see how the world evolves given our action. But we do not have yet a way to evaluate this state, like to say, oh, this is a good state or not. Like the VaViM will be able to model that we crash into the car that comes right into us, but it doesn't have the capability to say this is good or this is not good.
Can it model whether it would crash? Because presumably you don't actually have video data of a crash, right?
Right now, no, but actually, it's
I'm sure it has the capability if you have that data. But okay, sorry.
Yeah. So this is possible with so that nicely that gives me a nice transition to NeuroNCap. So NeuroNCap is a work from that has been published by people from Zenseact, and it's basically a nerve-based simulator. So that really did allow you to do crazy things like crashing into car safely. Basically, so it takes here you have a sequence from your scene. You first remove all of the dynamic elements in the scenes, like the cars, etc. And you learn a nerf on this, which gives you the static, which allow you to render the static part, of the scene from any point of view. What NeuroNCap does additionally is that it integrates here neural assets, which allows the framework to test you into different situations. So they have 3 scenarios. One stationary, that is where they just put a car or a bus or a cyclist in the middle of the road that does not move, and well, you have to avoid it. The other one is frontal, when you have a car or a truck that comes on your lane, really in front of you, towards you. And the last one is side, which is similar to frontal, but well, it's from the side. And it's quite realistic. So of course you have artifacts from the nerf, but this really allows you to release a pipeline really from images to action, and to verify when you are crashing or successfully reach your goal destination. And so this could be a way, for example, for us to get data and to train, let's say, with a reinforcement learning pipeline. We are really interested in the work that is called which does this. So on simpler environments, but it provides us with really, I suppose, well, the complete framework, where it's a combination of TD learning, when you have learned actually, well, this value network, which allows you to say this state is a good state and this state is a bad state at train time, and at inference time it's combined with MPC, where once you have a learned world model and a value model, it allows you to explore different features and course of action and select the optimal one. Yeah. So that will be the next step.
Yeah, this is really fascinating stuff, I think. Yeah, I guess the NeuroNCap is the missing part where you to generate the actual, to give you that well-formed value distribution, because you need that value function to be able to do this. Cool. Okay, that answers. It's very interesting. Excited to see how that goes for you guys. Is that where you're kind of actively working on next?
So first, what we need to do is to get. So here the issue is that you need to sample for many features, and currently we have a very big network. Like the VaViM one is quite big, and also its its representation here, it's quite big. So here one image is represented by almost 600 tokens. It's already smaller than the initial resolution, but it's still too big. So that means even for a big sequence with several frames, we can reach easily several thousands of tokens. And so if we want, so that's only for the context, but if we want to explore different features across more or less long horizon of time, well, this will be too expensive to do at inference time. So we have to find a way to first reduce, for example, the number of tokens, well, to get this representation really more compact and for us to be able to explore different features very efficiently.
Could you just train a new tokenizer that uses like a larger receptive field or something? It's like naive like that, or
Could be, yes. For example, I know that I don't have the name in mind, but I know that there are some startups or research labs that work on world model for video games.
yeah.
And they have like a 128 reduction ratio.
Is it video pre-training? Is it the one on the Minecraft? Is that the one you're talking about?
That's another one, I think. Or maybe, no, maybe you're right. Maybe it was this one. I don't remember. But indeed, I think we can compress even more. There is another alternative because here we are having a generative pre-training. I'm not specifically attached to it. For us, it was just a way for us to familiar with how to train big model, how to scale them, which is a skill to obtain already. But and also yes, it was already let's say a proven framework. Recently, you have also I think it was this one, Dino. No, Dino. Sorry. This work where instead of they use a Dino representation, and they use it as a forward model because really its core, you really want a representation, a state of the world that is as compact as possible, and that represents at least what you need to do your task. So for us, it's driving. And you need a forward model, so-called world model, that will take the representation, this state at time t, and try to predict the state at time t+1 given your action. But you are completely free on what this state should be, as long as it holds the information that you need to drive and be whatever you. So
Yeah.
yes.
Let's see. The problem is that involves moving from like that involves changing your parent training regime right away from this kind of pre-training heavy structure, right? Because like you don't know what's necessary for driving. One of the advantages of the transformer kind of architecture you're currently using is that like you don't one of the big innovations that I think has enabled transformers to work so well is that they don't need to do this compression, right? Like it's just a big difference from what you currently have, right? I don't know. It's a really interesting question as to how well this will work. Like even the people who use like Dino V2 features generally for like robot learning generally don't generally use them on the token side, right? That's
well, Gaia 1 also use Dino V2, but to distill into their VQGAN representation. So it's true. I don't have. Well, for me, it's still an open question in how to do it.
Absolutely.
At least
I think
how
it's
more efficiently.
Yeah. No, I think it's very honestly brave to talk publicly about what you want to do before you actually do it. Most people don't do that, so I think it's.
I'm really quite passionate about this. So we'll see how it goes. It's not clear yet if there is there's still a lot of work to do, at least on the simulator side, and how to bridge it with an RL pipeline. It's not easy. So there are still many research questions in between, let's say.
But it's a really, really fascinating area, really cool work. I think it's especially Actually, like the neural rendering stuff that you're mentioning is a nice bridge that would fix this value problem, right? Like it's because it does seem like that's been what's kind of missing for getting these kind of world model approaches to work, is like, how do you actually characterize that value function well? And great idea.
I think
Interested to see how it
that Wave,
works.
for example, have something similar that is called Ghost Gym. They have something similar. Well, that's not this one. So it's really nice to have it at least open source, because so far this kind of tools has been also closed source. Like Wave has this Ghost Gym simulator. Wabi has a Unisim, and now the last one, I think it's from Horizon Robotics, where they have it similar to NeuroNCAP, but they use Gaussian splatting, and they use it to train with RL and imitation learning. So that here on the left is totally generated from their simulator. So here it's really, you have entire scenarios with multiple moving agents. So of course you still have many artifacts, but I think it's already a step above.
Yeah, definitely. Yeah, this kind of recipe where you do like nerfs or Gaussian splatting and bring it into simulation is it seems to be much more like Waymo also has a few papers on this topic, and Google DeepMind had their little, on the humanoid side, Google DeepMind had their little robot soccer paper, which was very cool, which also was Gaussian splatting lifted into simulation for RL. So like these having open source versions of this recipe seems extremely valuable to me going forward.
Yes, I agree. I hope the community will move toward this kind of tools and benchmark, because another part, so we can come back to this open loop vs closed loop evaluation. So typically what is measured with closed loop evaluation is how close the prediction of your model is to pre-recorded trajectory, which is actually what the expert did. And with this kind of metric, you are actually penalized if you deviate from it, which sometimes it can be valid. Like if your expert goes right and you go left, but it may still be a perfectly valid and safe option, but you are penalized from it. So there has been in the community almost an optimization of this kind of metric, but they do not translate well actually to closed loop evaluation, where you are in this kind of environment, you act and you have feedback from your sensor. There are actually some work that show that first there has been one work that showed that you do not need actually some images to have good results on open loop metrics. They only use the proprioception inputs. And another one showed that you actually may have inverse correlation between open loop and closed loop performances. I think it was on Carla. So Carla is a synthetic simulator that uses a game engine. And so I'm really happy that we see more and more evaluation on the closed loop benchmark, when we can actually compare directly on the end task that is driving. As imperfect as these benchmark are, they are going in the right direction.
Yeah, absolutely. Why do you think there would be an inverse correlation between open and closed loop evaluations though?
Because the more you are better, it depends on how you trained. But at least, for example, again, sorry. So we did some scaling experiments. With VaViM, we trained entirely with imitation learning. Well, this is the first step. Imitation learning is the simplest approach to get our network to act. And what we did,
but an open loop evaluation would be something like reconstruction accuracy on a trajectory, right? As opposed to simulation. Okay. Just
exactly
there.
So you see that as we scale, we get better and better. As we scale both the data and the model size, the metric is reducing, so which is the correct direction. So it means that we are better at predicting what will do our expert. But when we pushed it on the closed loop evaluation, we saw that as we scale, so here the darker the point, the bigger the model is. And this is for different point of data each time. Different size of pre-training data. So as we increase the amount of data, the collision rates increase. So this was quite unexpected because, well, usually the bigger the model is and the more data you train on, usually the better you are, which was not the case here. The collision rate increased as we scaled, and this is because the model became more and more rigid, actually, because let me show you some videos.
This is like it's overfitting more to the expert. It's overfitting more to the expert data. So with covariate shift in reproduction, it like diverges, and it can't handle that. Is that kind of what I guess?
Yeah,
that's the idea.
Indeed. So here, well, for example, this one we don't know. Maybe not a good example. I think I don't have one here, but here we have in red. It's actually what the expert did in this scene, which is used as a guiding signal. It's like your GPS route. This guiding path is given to us as a high-level command, which can either be turn left, turn right, or go straight. The command always tries to get you back on the guiding path. So if you steer left, the commands become turn right. And if you go right, well, the commands becomes turn left. And as we scale, it seemed that, so here, well, let me give, with this one, for example. So this will be a good. So here it avoids the truck successfully, but as we and comes back to its lane. But as we scale the model and size, for example, on this particular scene, the model tries to stick as much as possible to the guiding path, which is what it learned to do during imitation learning. Just follow the command, because in this particular setup, a new scene and new plan, the guiding path is actually derived from the expert demonstration. So you never see the expert deviate from the guiding path, which is an issue in our setup. So that means as the more because here you have the model has a diverging choice to make. Let's say it has to not listen to the command to avoid the obstacle.
Yeah, this is that's really interesting. I mean, this is quite a common thing, or it's a really interesting problem that comes up in these cases. Cool. That's a very stressful video to watch of the truck coming directly at your car.
Yes, indeed.
Yes.
For example, in Carla, you have a diverging path between. So here, that is what our network did. But during expert demonstration, you will have data where you have the guiding path. Well, it's a GPS, right? It doesn't know about obstacles, so it tells you to go right through it. But the expert will deviate from it, avoid the obstacle, and come back. We do not have this kind of example in our data because the guiding path is derived from the expert demonstration.
Got it. So so this is purely a data problem then. So you would expect to see, like, if you had more data so the guiding path is from like a global route planner, right? So like if you had a more diverse data set where there was more deviations from that, would you expect this to work, or do you expect it not to? Or are there still issues where you would expect it not to succeed even with more data?
Hopefully, it's not clear yet. I will not give a definitive answer on this.
Yeah,
Florent, I'm curious. Like, would you say if there's a data set that is, let's say, similar to OpenDV but just frontal camera, a video, much smaller in scale, but consists only of crashes? So just video clips of crashes. how would that such a data set like be able to fit into the kind of paradigm that you're working on?
This could be interesting as we could learn, let's say, a classifier on crashes. So we will have data from the OpenDV where we don't have any crashes, and the dataset that you propose, and let's say we could learn a binary classifier on it, which is a crash and no crash, and we could use it as a value network, for example, to this network will take the state of our world model and learn to classify and say, okay, this state is actually a bad one or this state is a good one. This could be used.
It would also presumably help you train your world model to like simulate what a crash looks like or the moments leading up to one, right? That's also, yeah, cool.
Yeah, I think it could be really useful because this kind of data is.
Yeah, another thing that I think is super interesting that like maybe OpenPilot or and Tesla clearly have is like the error recoveries, like where the policy went wrong and then you get back onto the main trajectory. I wonder if there is an equivalent. I assume there's no equivalent data like that because that would also presumably really help with all learning these like world models and associated value functions and policies and all of this and reduce the issues that you're showing here.
And also they have it's really impressive what they managed to do because they are also acquiring human supervision at scale, like without having to explicitly pay people to record the data. So there is this paper called with human in the loop again.
Yeah, human in the loop reinforcement learning.
Have you seen it? Yeah, it was this one.
I'm not sure which specific paper. Yeah. I think part of the value here is it's like getting these corrections, right? So making sure that there's because I think helps solve, in the reinforcement learning case can help solve the issue where like exploration is very difficult and getting like the perfect exploration to get a really precise thing can be really hard. But yeah,
indeed. It allows you to spend more time in situation where it's useful actually, because if your policy goes too far into and doing I don't know things that you don't want to do, like being stuck on the tabletop or whatever, you can just intervene, correct the trajectory, and take it back in a situation where it handles it better. And then the entire trajectory, both with policy prediction and your intervention, becomes training material to show that, okay, look, this actually is a good, the entire thing is actually a good prediction for your policy. And at least that's how I see it. Tesla can do it at scale, where if their policy, like with this FSD beta program, it runs, and at some point the human is not confident at all on what the autonomous system is doing, they can take over. And the fact that they take over, like they take back the wheel and the gas and brake pedals, all of this can be recorded and used to train and improve the system at scale.
Yeah, it really is it's a very elegant flywheel for improving driving, honestly, that they have this where you just have like, and the person has to take over because they're in the car. Yeah.
For sure. Yeah, it's really not just camera data acquisition. You actually have really strong signal supervision on your policy. So that's really strong.
Yeah, presumably, I'm guessing in Tesla case, like I'm guessing like at this point, I mean, because of the bandwidth constraint or maybe the data storage constraint, I'm guessing they only probably send over like short video clips or like, maybe a few seconds, maybe 10 seconds when there are like, crashes or disengagements. So if you think about those are likely just like real world failures, right?
But those are
So in a sense,
but that's the most valuable data is like the few seconds right before the disengagement and the few seconds after. Like that's what you need.
Yeah, exactly. But my point is that it strikes me that those are all, in a way, they are learning from negative demonstration or like failure cases. Whereas like, all this data set that we are, could be OpenDB, it could be the new scenes. Like those are successful drives. But maybe the paradoxical thing that is like beyond a certain point that there's not enough that you can just learn from successful drive. You actually just want to see how it feels.
Well, yeah, I mean, I think this is what's like, you have, first of all, Tesla has millions of hours of driving, right? Like they've already got the successful data set, right? So, but like after a certain point, if you want to improve a model past a certain threshold, you're doing like, there's a lot of words for it in machine learning, right? There's like hard negative mining to find the examples where your classifier fails at. There's Dagger to help resolve the covariate shift issue, right? There's all of these kinds of things, and this is at some point, if you want to get high performance, I feel like that's what you need to do.
Yeah. So I'm wondering like how would having, you know, some of these tools that Florent you pointed out, what's the one called, Nerve something, basically creating alternative like world, like kind of in simulation. Like, how would having those kind of tools enable you to maybe get to, it's not real world failures, but maybe generating like possible failure cases so that you can maybe in effect get the same thing that Tesla may have without having like millions of cars, you know, in the real world and actually crashing.
Yeah, for sure. I think people working on this kind of simulator are going toward this direction because at the core of the simulator, you have a big nerve for Gaussian splatting, Gaussian splat for the static part. And then you have neural assets for the dynamic part. So, and those neural assets are just like boxes in the bird eye view that could be controlled by an oracle policy that have privileged information of the scene and control all of the agent of the scene, for example. And you have works on this, I think, from Waymo or other. And you also have, I think it's called Scenario Dreamer or something like that try to really generate the scenario for you for the the position of the agent in the scene. Then I guess you could have like also some I don't know how far would it go in such simulator, but with a self play, for example, like Alpha Zero or this kind of approaches could be applied with this. It's just that in all cases, it's difficult. Well, we don't know yet how to properly define what is correct driving, to formalize it either by rule or learnable prior, like we could leverage pre-trained VLM, for example. Getting for this, for example, with this human in the loop reinforcement learning, it's also a good way to integrate implicitly what good driving is by letting the human intervene at whenever the car is not doing the right thing. So really saying that this is good driving and this is bad driving is quite hard, actually. So even if you have a perfect simulator, getting a proper reward and to train your model is still difficult.
I think the other challenge could be also like, even if you have a really good like basically simulator or world model, what scenarios to simulate is also another big challenge, right? Because in theory, the exploration space could be maybe nearly infinite. You know, could be different type of cars, different sizes of cars. Like so many different scenarios could happen in that 1-2 seconds.
Yeah.
Yeah. Have you thought about like, you know, how you guys may be able to use these tools? Because I think the promise of simulation is that it can speed up time. And when things fail, you don't have the costly, you know, you don't have people die in real crashes, especially for self-driving. But the question I always have is like, you know, if the exploration space is so huge that despite your ability to speed up time in simulation, you're still not really fully exploring the full vastness of the exploration space, then it's still, do you have some thoughts about what I said just now about this?
Yeah, so that's one, because indeed with a simulator, well, you have to still simulate everything, especially to have sensor feedback. I think the ultimate goal of world model, as it has been described by David Ha and Schmidhuber in their paper, well entitled World Models. The ultimate goal is to, the world model then is an internal simulator, right? An implicit simulator in this abstract space. And the idea will be to directly train within it. which could be very fast. So I don't know if it's always risky to make this kind of parallel, but sometimes as human being, we are able to imagine different scenarios and at least plan on how we could react to certain scenarios. And a perfect world model would allow you to do this. We are not there yet in terms of generalization, composition, because one capacity that the network currently, the kind of model that we have currently do not have, is they are very good at picking up statistical regularities, but we don't know really yet how to then form different form of an abstraction from it. Like as a human being, I've seen a certain amount of object fall, and now that if you present me a new ball that I've never seen, like with really weird ball, like with spikes and flower pattern, whatever, I know that if I drop it, it will fall on the ground and stay on the ground. So I have abstracted the concept of gravity and rigid physics. And currently, we really don't see this kind of behavior, at least in the so-called world model. I have interesting benchmark on this. It's called Physics IQ. I think it's from DeepMind. And the other one is called Phigen, where they specifically test this kind of video model, so-called world model, to test this kind of capabilities in this kind of models. Well, they fail.
Well, do you have a sense of, I mean, if you were to guess, what level of data would you need to train, I think as you just spoke about, like a near perfect world model?
I don't think it will only be an issue of just scaling data, but there will be something more about really the system or the kind of model that we use. I'm particularly interested in the ARC challenge from François Chollet, who specifically tries to address this, where you have new problem that you can't overfit. You can't have overfit on it because it has been completely generated from basically comes from a new data distribution. So 3 things to take back from the paper. Well, first, we open source everything: the code, the training code, the evaluation code, the weights. And so that's something that is really open to the community. So I really encourage researchers interested in this kind of topic to test this model, to really open them, see what are the features, what has been learned, how they behave, show how they fail, and try to improve them. The second one is that, it's a promising approach. So in the different benchmark, specifically Neuro and CAP, we show that compared to classic approaches, so for instance, UniID and VAD use a bird eye view representation, where they use a significant amount of hand-labeled data or human annotation, like the position of the car in the scenes and their track, as well as the HD map. And we show that without using any such thing, we are competitive. And we actually sought on the frontal scenario. And the thing is that we only use the frontal camera, whereas UniID and VAD use all the camera in the available, the side one. So here it's also part of the reason that we have such bad score on the side scenario, just because we can't see the car coming toward us. Yeah. So that's really a very promising approach, I think. And next, indeed, I would really like to see this kind of work going toward to moving from this imitation learning pipeline, which is really the result is really a reactive policy, and go toward this planning-based, world model-based approach, which would, I think, would allow us to solve this kind of benchmark. And then it will just be a matter of improving the simulator and the model itself.
Very cool. It's nice to see lots of open source code, great results with end-to-end models, all that.
Yeah, thanks.
Maybe for we talk about this like a couple of times now. I think it's great that you guys like open source, basically everything. Although I would say like one thing just to highlight is that I think with role models, the compute needed is, in my view, non-trivial. So I think that's just something to highlight. Like, could you like speak to that a little bit? Like, how much compute did you end up using?
The biggest one was trained for 20 hours on 200 800. So it's clearly a significant amount of compute. That being said, we really wanted to push the thing, and first it was really a good learning for us. And then you can already obtain really interesting results with, we already with our smallest model, we get very good results. So in terms of research, it could be already something. Well, you still need a couple of 800 for sure, but it will not be at the scale of 200 GPUs. But for sure, it's expensive. That's also part of the reason we want to, in an ideal case, well, it's not for a near future, but move out from this kind of pre-training because it's so expensive.
Yeah, but I suppose as you maybe continue building all this work, I suppose one of the dimension you want to explore is just maybe continue to scale on the data side of things to see how far you can push. So, and I guess probably the compute will still, at least on the pre-training phase. Yeah, but I guess that's just the nature of the beast, I suppose. But anyway, I mean, still really cool to see you guys open sourcing everything, so people can poke at it. Yeah, so I guess maybe the usual last question that we want to ask is like, give a shout out to some cool papers that you come across, but it seems that you share so many papers already.
Yes.
Yeah, I guess, well, maybe do you have one last paper that you really want to give a shout out to before we wrap this?
Yeah, I think I can. It will be, I really like this one. It's called an study of photoregressive pre-training from videos. And where they really scaled autoregressive network. So in this case, they use a llama. The work is from Meta and Berkeley, and they scale it to really trillions of video tokens, and then they fine tune it on different tasks, whether it is specification on some robotic task. Yeah, the paper is really complete and well written. The thing that was interesting to me is that even though we are at this scale, when they evaluated on an image depth for a discriminative task, we are still far from models like Dino V2 when we have an 11 point of difference, even with the larger model. And so, of course, Dino V2 has been trained specifically on a discriminative pre-trained task. So certainly it may favor, but there is something with video generative pre-training that bothers me a bit in terms of really representation learning, and I don't know yet how to improve it, because even right now, when you look at Gaia 1 still and even the second version still distill Dino V2 in them, we will certainly do it at some point. And so when we look at semantic evaluation too, we are still far behind Dino V2 features. So it's something that I really would like to look into in the future.
Awesome. Very cool. Thanks for the shout out.
Yeah, I guess, Chris, do you have any more?
No.
Yeah.
Thanks for joining us.
Okay.
Very, very fun discussion. Lots to think about. Good luck on the future projects. Like I said, I think it's very brave to lay out what and how you want to do before you do it, because things can change. But looking forward to seeing more from you.
Yeah. Well, actually, if someone managed to do a model that is really efficient, fast, compact, I would be happy to have it off the shelf and build on it.
Yeah, awesome.
Very cool, very cool. And I think I would love to eventually see an actual VaVAM 2 or 3 that's actually evaluated in a real world car. I think that would be really, really the real test. Hopefully many real cars. But anyway, yeah, thanks so much for your time, Florent. Yeah, really keep it up, man. There aren't that many teams that I know of that are doing what you're doing, and open sourcing. Thanks for sharing your work. I think it's really good.
Welcome, my pleasure.
Okay,
Great.
Chris, what have you learned?
So I learned a lot about video generative world models and you have to use them for robotics. I think it's really cool to see. Like we've seen a lot of these exciting early results, but it's nice to see someone able to train driving policies based on them. It's really nice. It was a very fun technical discussion of where this can go and what the weaknesses are, and like seeing a much broader view of like the research, the literature than we usually have in these talks, because we spent a lot of time chatting about the future and related work as well. But yeah, great stuff. What did you think?
Yeah, I think world model it's like it's a very different paradigm, but still kind of like basically another way of doing simulation, you know. And unlike, let's say, simulation engines that are very, let's say, have high fidelity to physics, they are basically just learning from data and learning some representation about the world. So it's like attacking the problem as a simulation, but very differently from like I imagine how traditional simulation have been done. So I think it could be a very interesting like direction of research. I do hope that more like I don't know whether it will always be the case that like it will be pretty compute intensive. If I'm not wrong, the kind of compute that he was using is non-trivial. I imagine most academia lab won't have access to those, even for like just for a couple of days. But you're talking about hundreds of H100, so no joke. So I think that might literally end up being a bit of a bottleneck in terms of like just having more teams to try.
Well, but hopefully though, people can share pre-trained models and weights like he is sharing his code. So like I think that's like I think that one of the values of these kinds of things would be if people could build on them, right? In the same way, like we mentioned Dino at the end, right? Whereas his
Yep.
Dino outperforms sorry.
Yeah.
But Dino V2 features are a fundamental backbone for a lot of these things. And there have been other things that have, I think, tried to supplant Dino as a better vision representation for embodied robotics. And to my knowledge, none of them have really taken. Although there's a new meta encoder set that just released that maybe could do similarly well or better. But anyway, but the point is, but basically, that would be a nice proof of life for these kinds of things would be if they can produce a generally useful set of features that could supplant Dino, right? And then that to your point about cost, though, that's something that people can use with basically no compute, right? Like then I can start actually building on this. And there was a bunch of questions there was a discussion about how you actually make one of these models work without like the huge token context length and massive transformer, and like that's also really because of course you can't really like that also seems really impractical. So like there's lots of stuff here that I think if this stuff works, like eventually for a car policy to work, it has to be able to be deployed on an edge device. So there's got to be something that you can do without a massive amount of compute, right?
Yeah.
I don't know.
Well, anyway, I mean, we should definitely get more, researchers doing world models. I think it's a very interesting, area of research. I definitely want to learn more.
Yeah,
Okay, cool.
definitely.
Let's
right.
let's do it again soon. Okay, right.
See ya.
See ya,
Bye.
Chris. Yep.